All right, continuing on with Chapter 3 videos, and in this one we're going to talk about combustion analysis, and more specifically, how do we get an empirical formula from combustion analysis? And what combustion analysis really is you take some sort of hydrocarbon and you burn it in the presence of oxygen, and then you analyze the products. Okay, so you know how much of your sample you put in, and then you know how much carbon dioxide and H2O you get out. So you can determine some information about your initial sample. So we're going to use the mass to determine the formula of reaction of the reactant. The reactant formula. Okay, so we have all this information about the CO2 and H2O, and we know that in our reactants, all we have are carbon, hydrogen, and oxygen. Great. So we can use that information to get the formula of our hydrocarbon. So we have an example here, an example problem. So a 0.2 gram sample containing just carbon, hydrogen, and oxygen is combusted, yielding 0.2998 grams of carbon dioxide and 0.0819 grams of H2O. Determine the empirical formula. So we have some hydrocarbon, so C, X, H, Y, O, Z, using X, Y, and Z because we don't know what those subscripts are yet, plus some O2, and we get some CO2 and H2O. Okay, it's a combustion reaction. Remembering combustion reactions are characterized by that reaction with O2. And when we combust a hydrocarbon with oxygen, we always get the same products, carbon dioxide and water. Okay, and so when we did this, we found out that our carbon dioxide was 0.2998 grams and our water was 0.0819 grams. Okay, so if we only had one reactant, we could just do a little mass conservation subtraction and just determine what the things are there. But some of that oxygen in the products came from the O2. So we need to figure out how much of each comes from where in order to determine our empirical formula. All right, so we're going to start by determining moles of carbon and hydrogen. And because we know that those only come from one place in the reactants, okay? And we're going to use that information to find out how much of the oxygen came from the O2 and how much of it came from the reactant. So I'm going to start with my CO2. And I'm going to find moles of CO2. All right, so we're going to start with going for moles of carbon. So we have 0.2998 grams of CO2. And we're going to use molar mass to get moles of CO2. Use molar mass. And remember, the units of molar mass are grams and moles. Okay, so if I have grams, I can find moles. If I have moles, I can find grams using the molar mass as a go-between. So our mass of CO2, so 1 mole of CO2 has a mass of 44.008 grams. Okay, and all I've done there is add up the masses of the individual atoms there. So 1 carbon atom, 2 oxygen atoms, and we get roughly 44 grams per mole. So we find that we have 6.812 times 10 to the minus 3 moles of CO2. Right, now to get moles of carbon out of that, I'm going to use the relationship of how many carbon atoms there are in each molecule of CO2. 6.812 times 10 to the minus 3 moles of CO2 and if there's one atom per molecule, that also means that there's 1 mole per mole of molecules. So I can say 1 mole of carbon in 1 mole of CO2. And it's nice when it's 1-to-1 ratios because the numbers come out the same. So now we know moles of carbon. Right, so that's an important number. We're going to keep that number. Now let's do the same thing to determine moles of hydrogen. Okay, we're going to use the same tactic, and we have 0.0819 grams of H2O, and I'm going to go to moles of H2O through molar mass. So 1 mole of H2O is 18.02 grams. Okay, anytime I need to go between grams and moles, I can use molar mass as my conversion factor. So I find that I have 4.5449 times 10 to the minus 3 moles of H2O. All right, now I need to eventually get to moles of just hydrogen. So I'm going to use that same tactic. How many hydrogens there are per molecule? 4.5449 times 10 to the minus 3 moles of H2O. And there are 2 hydrogens per molecule, so 2 moles of hydrogen per mole of molecules. Or you can think that there are twice as many hydrogens as there are molecules because there's 2 hydrogens per molecule. So we find that we've got, looks like 9.0899 times 10 to the minus 3 moles of hydrogen. Now we want to keep track of our sig figs. So in our moles of carbon, that sort of takes care of itself. But in our calculation of moles of hydrogen, I'm tracking at the 3rd sig fig. So when I get to moles of hydrogen itself, I'm still tracking at that 3rd significant digit. All right, now, what I want to do now is get to mass of carbon and mass of hydrogen. Okay, because that's how I'm going to find out what mass of oxygen came just from the sample. All right, so I've got 6.812 times 10 to the minus 3 moles of just carbon. So what we're doing is we need mass of carbon and hydrogen. Okay, so I need to get from moles of carbon to grams of carbon. So 12.01 grams of carbon in 1 mole of carbon gets me 0.0818 grams of carbon. And then my hydrogen, 9.0899 times 10 to the minus 3 moles of hydrogen, and it's 1.01 grams of hydrogen in 1 mole of hydrogen, will get me to excuse me, I had to look it up, 0.00916 grams of hydrogen. Right now, our sample, we were told in the problem, was 0.200 grams total. Okay, so that means that the mass of carbon plus the mass of hydrogen plus the mass of the oxygen equals 0.200 grams. Right? If I know the carbon and the hydrogen, then I can find out how much oxygen was in just the sample. Not the O2 that it is combusted with, but how much is just in the sample. Now remember, coming back to our equation, which is way up here, we've got some oxygen in the sample and some oxygen as the O2, which some of each went into that oxygen and that oxygen, right? So by finding out the carbon and the hydrogen and knowing the original mass of that compound, I can find out how much oxygen came from just the compound by itself. Let's come way back down here. And we find that with our carbon we have 0.0818 grams and our hydrogen 0.00916 grams. And so our mass of oxygen comes out to be 0.109 grams. Right, now eventually I need to have everything in moles so that I can do my empirical formula thing. Right, so I'm going to take my oxygen, convert it to moles, we'll find that we've got 6.815 times 10 to the minus 3 moles of oxygen. Right? Now it's an empirical formula problem just like any other. Okay, whenever we're dealing with empirical formula, we get everything to moles and then we divide by the smallest moles and then we work it so that we get whole numbers. Okay, so it's once we get to this stage where I know moles of carbon, moles of hydrogen, moles of oxygen, it's an empirical formula problem just like any other. All right, so we're going to take to our new step, divide by the smallest moles. Right, so we already figured out the carbon, the hydrogen, and then we just figured out the oxygen. So we've got 6.812 times 10 to the minus 3 moles of carbon, and we've got 9.09 times 10 to the minus 3 moles of hydrogen, and we just calculated 6.815 times 10 to the minus 3 moles of oxygen. All right. So 6.812 versus 6.815, we could pretty much divide by either one of those because they're only differing in the, the 6th decimal place. But I'm going to go with the one that is actually slightly smaller. And we end up with a 1.33, and a 1. All right, so I need them all to be whole numbers. So I'm going to multiply all by 3. And I'm going to end up with a 3, a 4, and a 3. All right, so our empirical formula comes out to be C3H4O3. Right, so this seems like a very long, sort of drawn out process. As I scroll up, it seems like it's a really intense thing. And really, these problems are easier when you only have to do with a carbon-hydrogen compound. When you have oxygen in the compound, it gets a little trickier. But the point is that we use our stoichiometry, we use our conversion factors to determine moles of the carbon, moles of the hydrogen. We use those to get mass of each of them so that we can subtract from the total mass and find out how much of the oxygen was in the compound. And then it becomes like every other empirical formula problem where we use moles, divide by the smallest moles to get whole numbers. That's going to do it for this video. When we come back with the next one, we'll talk about how to get molecular formulas from empirical formulas.